Okay, so this is where we left last time. So next step is to change the mesh density. Okay, so next step what we will do is we will copy this study. I will copy this over, and basically this tells you the source. So right now the source is the original notch bar for the draft case. So now I will copy this over, and I can give this any name, but I will keep the name similar to the one that I have here. Okay, so that I can keep a track of what I'm doing. So I will now be doing high quality mesh, but with coarse size. So I will just copy that name. I just added notch bar before it to differentiate. So notch bar high quality mesh with coarse size. Okay, and I'll just keep with the default configuration that was there. It is still a static analysis, so no changes. Clicking on this arrow will select the will copy this over. So now this one over here you can see is the new analysis file. Okay, so let me share it with you. Okay, I hope it's shared now. Okay, so this one now here is the new analysis file. By if you right now it has copied everything over, but because we are going to change the mesh, therefore the results files will be overwritten. Okay, they will be deleted first, and then we will, when we run it again, then it will be overwritten. So I'll go on to the create mesh tool again, and it will ask me, do you want to delete this old mesh? And I'll say yes. And I will now go to the mesh quality, move this from my draft to high quality. And I explained to you the difference between the high quality and the draft last time is basically the number of the nodes and the on each of the elements. So let's say if this was one of your elements and it only had these end nodes, right? So the nodes were only on the vertices, but now you also have mid-side nodes, and it can even be on the faces as well, more nodes, depending on what exactly type of the element is. For that you'll have to go back and check in the exact details in the SolidWorks help files, but essentially the number of nodes increases, and that allows you to change the level of approximation. Okay, right now they are still linear elements, but you can have high quality elements with non-linear behavior defined as well. Okay, so now we just simply move this to the high. Then going back in the definition, we move this to the coarse, right? So meaning the biggest element size that will be possible, and you can see the change of the element size here. Again, I will stick with the standard mesh. Okay, I will stick with the standard mesh, and you can see here that the element size for the standard mesh, if I move it to coarse, becomes 8.55 on one of the edges. So with these changes, I will now click on the green tick to remesh the model. You can immediately notice that the size of the elements is much bigger, and the total number of elements is actually smaller. You can view these details by going into the mesh, right clicking and clicking on details, and you can see the total number of nodes is 1902. So this becomes 1902. So the number of nodes have reduced, and the number of elements has reduced to 1027. So 1027. Did you notice something here, that now for these 1027 elements the nodes are 1902, meaning per element the nodes have increased, although the total number of nodes has reduced from this, but per element the node number has increased, and that will also affect the results. So let's now plot the results by running the study again. All of these graphs right now have invalid results basically, because they belong to the last study. So we have to run the study again by clicking on run this study, and now the analysis has been run and it is showing us the updated plots. Any changes that you made, for example, in terms of the scale, will automatically be preserved in the next run as well. So now you have got Sx, which is the x direction stress, and you can see here the maximum value has now moved up to 159.14, and previously this maximum value was 120, right? So your maximum has gone up 159.14, and your minimum has changed as well. So it is minus 16.16, but I have not asked you to record the minimum, but it's good to know that that has also changed. Then you have got maximum displacement along x-axis. So that displacement can be obtained from the displacement plot, which is 4.804 into 10 to power minus 2. So I can actually ask it to directly give me the number so that I have it clearly exactly which location it is. And if I go on to the chart options, I can ask it to show minimum and maximum. So minimum is at the support and maximum is here at the loaded edge, right? So it is 4.804. Okay. So 4.804. So you can see there is slight increase in the displacement as well, right? Now with this, then I have basically concluded. I've asked you to actually calculate margin of safety here as well. Okay, so you can calculate the margin of safety or factor of safety in this case by taking the strength. In this case it is a ductile material, so I'll choose yield strength. Yeah, so yield strength and dividing it with what? Hello. No, because this is the margin of safety. Look, this is where you have to think about it. It's no longer allowable. It's about the actual maximum value of the stress, because this is the context is you are trying to figure out whether this is safe or not, or how safe it is, right? So this is the context of margin of safety. So divided by actual maximum stress. Okay, so this now you can easily define Okay, I'll just keep it with in this format right now. I'm not, because I don't want to spend too much time. So what is now the actual yield strength in this case? How will you know that? You can go back to your material definition, and here you can look into the yield strength value, right? So in our case, the yield strength is 351.571. So 351.571 divided by, what is the maximum stress? 159.14. Okay, I'll copy this formula over here. So how much is this now? 2.21. So that's the margin of safety for this particular component. Okay. From the point of view of the previous analysis, again this 351 will be still the same, isn't it? Because it's the same yield strength, but the actual stress was 120.15. So what was the margin of safety? 2.926 or 2.93. Okay. So this is now, if what I'm trying to say. So this margin of safety, therefore, you can see is misleading, isn't it? Because in actual, the other mesh has shown that probably the stresses are even higher. But we are not sure if the stresses are really, even this is a correct number or not, right? So what we are going to do, we are going to run the analysis again, but this time with the, instead of course, we'll go for default size, okay? So we'll go for default size to see. Now, next basically step therefore will be, I will again run the analysis, copy it again, okay, and this time give it the name, new name, just like previously. So this is now exactly same, okay. Again I will need to redefine my mesh, so I'm now here, recreate my mesh with now this one. I'll just show you. So keeping the same standard mesh, keeping the same high quality, and now just simply resetting it to the default size, right? Which changes then the edge length to around 4.27. Okay. So with that accepted, I rerun the analysis. You may notice slightly that this time it took slightly longer, and now the mesh density is much higher because the sizes of element is smaller. We can note how much exactly is the change by going into the details. Total number of elements is 6,444. So total number of elements is 6,444, and total number of nodes is 10,627. So you can see now there is a huge increase in the number of nodes, almost 10 times. And now this is also at high quality, so 10,627. Now let's see what is the effect on the actual results. So we will rerun the analysis, run the study again, and you can see now it's taking a few more seconds for it to solve because of the greater number of elements and the nodes. So now you can see here, if I go back to stresses along x-axis, that my maximum stress has actually increased, okay, and it has gone up to 169.6, okay. So this becomes 169.6 megapascals, and the minimum has of course changed as well, but slightly, okay. Similarly, you can see the displacement has changed, but very little, 4.812, okay. So the displacement has already showing signs of convergence, meaning that it is converging to a singular value. The stress is still changing quite a lot, right? But again, in terms of percentage change, you can see that now this change is much smaller as compared to the change between the two, right? So meaning that the slope of that curve is flattening and it is becoming straight. So this one is now 4.81 to E minus 2 millimeters. The margin of safety can again be calculated. 351.571 divided by, so this becomes 2.07, and again now you can see here that the change in margin of safety is also reduced, right? So let's now do this one more time for high quality mesh with a fine size. So when we do this, we go back and we again copy our study. We give it the new name. We save the settings. We go into the mesh. We again create the mesh. We delete the old mesh. And now we keep the settings still standard mesh. quality high, and size the fine size on this one. So basically the smallest size that is possible with 2.13 mm length on the edge. We click OK, and you can immediately see it has taken much longer for even to mesh this structure, but now the mesh is much more refined. And if you check the number of elements, then what you see is that you have now got around 80,860 nodes. So I note down this value, 80,860 nodes, okay, and 54,689 elements. So 54,689 elements. Now, if I again run this study, I'll be able to calculate the results, but you can see here it's taking much longer, okay, because of the greater number of elements. So now you can see here that the stresses are much more refined, the bands are much more clearly defined, and now we have got a very high stress, which is 177.18, okay, and the minimum has also reduced significantly, you can see, okay. So this becomes 177.18, and the displacement becomes 4.815. So the displacement has not really changed much, right? It's very small change, 4.81. So up to fifth place of decimal, there is no change, right? And then you have only some change. So the displacement has precisely converged. The stress has not precisely converged, but it is also looking that it is converging based on the increase of number of elements. So again, if you want to calculate the factor of safety, you can do that by simply dividing this with maximum stress, which will be 177.18, and this will be 1.98. Okay, so you can see here that the actual factor of safety was probably, yes, so it has reduced and it was probably less than 2 in this case, right? So then I asked you to actually plot these numbers using Excel, okay, so that you can see the trend of convergence. But then I will also do one more case after this, okay. So let me very quickly again, I'll let you tidy up the graphs later. So I will just plot stress, number of elements. In fact, I think I can copy that over, can't I? I can simply, I hope it will let me copy. And right. Okay. Okay, I think it's copied, but it's merged, so it may have difficulty plotting it. We'll see. So what I can now do is I can basically sorry, how much was this number? So now I will just simply try to plot this using a scatter plot. Okay, add So on the x-axis, I will plot the number of nodes. Okay. Now, ideally, you should only plot the convergence plot for the same type of elements. But I will also plot right now the draft mesh quality as well on the same plot. Okay, just to highlight some of the changes. So the y-axis in this case is maximum stress, and you can now see here. Okay, I think because it is, I'll have to copy separately the file, the data, because otherwise the data is not clean. So okay, so let's now right. So let me now quickly, hopefully this will now allow me to okay. Yes, now it's copying correctly. Okay, right. So let me now plot the graph. I'll plot on the x-axis the number of nodes, and on the y-axis I will plot the stress. And this is basically, you can see here a trend emerging that in the initial change, just with the size, basically this one is showing you the effect of change of element type, but then is the effect of changing the size of the element. And what this graph is actually showing you is, and you can probably connect it using a smooth line as well if you want. Okay, so now you can see here. So you can see here, for such a huge change of number of elements, there is only very little change in the stress values. So this is now where judgment comes in. Now you can use precise formulas to calculate convergence as well. So for example, some people have suggested taking the difference of the last two levels and calculating the percentage change in stress. And then if the percentage change in the actual value of the stress is less than 5%, they will accept the values to be converged. Right now, I'm not too much worried about precisely defining the criteria. That can be based on your company's guidelines, or it can be based on the on a research work that you are studying, that what is sufficient for you. But right now I'm trying to explain to you what do we mean by the convergence, right? So this is what we mean by convergence, that by changing the elements by almost, you can see here, the number of nodes are changing by 8 times, right? Yet the stresses are only marginally changing, right? So this is what we mean by convergence over here. Okay. Now imagine that if you had to do this kind of a mesh size for a large part, right? Or part with complicated assemblies, multiple components together, then if only this small bar had to be meshed by 80,000 nodes or 56,000 elements, what about a large part that will have millions of elements then, right? So that is not going to be computationally efficient. You will need a lot more computer resources, and maybe very soon you'll run out of your computer memory. So what's the solution for that? The solution is to have what we call as controlled meshing. Now different softwares allow different ways of this controlled meshing. The method that I am showing you here is applicable for SolidWorks, but in other softwares the same thing can be done, but maybe in a different way. Okay, each software will allow you to do it in a different way. So right now what I am doing is I'll start with so basically what it means is that we will selectively refine our mesh. So right now this mesh, if I plot it again, right, is almost uniform throughout, right? Now what we will do, we will actually go back to our chorus mesh, which was this one, right? Right? It was this one, but we will selectively refine it for these edges, right? We know that where the maximum change of stress is happening. Okay. Now, with this, let's go back to the chorus mesh case, copy the study over, and I will give it the new name, and I will call it as high quality control mesh control with mesh control. So high quality with mesh control, and I select OK. Now you can see immediately the mesh is right now will be the same as what you had before, but now we will apply mesh control. Now again the steps are also given here in the, sorry, where did it go? Here in the step-by-step guide. Okay, so basically what you'll need to do is you'll need to first select the edges around which you want to have the mesh control. Okay, so basically after this I will go click on apply mesh control, right? So let me do that. So I'll go here, right click and say apply mesh control. Depending on the version this may have moved slightly, okay, but I think for all of you the same version should be there. Okay, apply mesh control. Now in the apply mesh control you need to select the entities on which you want the mesh control to be applied. So we can apply it on these edges, so this edge, okay, and top edge. Is he also doing it for the top edge in the book? I can't remember. Let me go back and check. No, he's not doing it for the top edge, but he's doing for the face. Okay, so to keep the things similar, I'll do that, but it doesn't matter really. I could have done it for the top edge as well. So, yes, but I'm saying that in terms of the edges, he's selecting it. Okay. So I select this surface, and then I'll go back because we want similar results on both sides. Okay. So I'll select now this edge, and this face. Now once I'm happy with my selection, I'll just tell it that which size I want. Okay. So what size and what ratio I want of the transition. So I think he's using a ratio of 1.5, so I'll keep it same. Ratio 1.5. Okay, and he's also explaining the meaning of this ratio. So basically this ratio is the geometric progression of the change of the element size based on this formula, okay, over here. So based on this formula, this will keep changing the element size. Does he move it to the fine or to the default for the? So I believe he should move it for the fine. Okay, he's keeping it on the default here. But you can make it for the transition from chorus to fine as well. Okay, so that's up to you what transition you want, and then you will be able to remesh the part. So let me just do. Okay, so he's doing it 2 times basically on with different mesh ratios. Let me go back.
It is mentioned course size.
Yeah, he started with the course size, but you need to specify what will be the density on this one.
Default or fine?
Yes, so we can go for either default or the fine, or put it anywhere in between that we want. But I'll just keep it right now for the default one, okay? Because I think because the reason he's going for default, if you notice, this number, right, 2.13, this is similar to the number that we had in the fine mesh when we had the fine mesh throughout the part. So he's trying to keep this number similar, the smallest element size, okay? If he wants, he can still make it even smaller if he wants to, but I think this will be enough. So with that, I just select OK, and now we need to mesh and run, or just mesh it first and then run it again. So I'll just mesh and run. Okay, and now if you go back, you can see the mesh. Can you see here now the difference? Yeah. That the refinement is only around this edge, okay, and this face where you need the maximum resolution of stresses, and this one is coarse. The results, if you go now to your stress, you can see here that the stress is somewhere between the very, very fine mesh and the coarse mesh, but with very few elements, and the time of calculation was also reduced. Okay, so the stresses are now 173.9. So 173.9. So let me 173.92. The total number of elements, so you can see here total number of nodes is 4688. So the number of nodes is only 4688. Can you see how much computational power you are saving? Here you had 80,000 nodes, here you have got only 4,000 nodes, yet you are able to get a result which is very, very close to the highest mesh size. Okay, so that's the main advantage of using mesh control. And the total number of elements is 2709. So is this point clear to everyone? 4.812. So you can see here that this is, in terms of displacement, is again very similar. So now you've got so how much is this now? The factor margin of safety? Margin of safety? It's 2.02. Okay. So this now shows you that this margin of safety is dependent on your method of calculation, isn't it? Right? So the more accurate you make, the more accurate margin of safety calculation will be there, just like the stresses and the strains. Right. Next, I ask you, any questions on this one so far? Right. So you need to do this by picking up any one of the other materials in the table, please, and the force. Yeah. Yes, like I said, I don't mind. Just take one material. Ideally, if you want to be practiced, then you 4 members can do one material each. That's the best. But I don't want to overburden you, so just take one material and compare it with my results for the stress concentration factor. Okay. So by the way, how you are going to calculate the stress concentration factor in this case after the mesh convergence? So did I ask you to calculate it here or no? I think stress here I asked you to calculate, right? Yes. If you're comparing it with mine, then attach my table if you want. Yeah, no problem. Okay. So Next, I asked you to plot the graphs here, so you can plot them in the Excel and bring it here. And after that, you will be now I ask you to get me some more detailed results for this. Okay. So maximum normal stress, you already know what this is for the from this case, right? So what was this? 173.92, right? So it was 173.92. Next, I have asked you to plot maximum normal stress along y-axis. So who is going to tell me how to plot this? Now I need maximum normal stress, but along y-axis.
So we do the force. Like,
Change the
we
direction.
turn the direction of the force and we change the fixed plot. No.
Anybody else?
Change from X to Y.
Change the coordinate system from x to y. Look, I know it's fine. It's fine if you don't understand this, because for us as an instructor, obviously, you know, a lot of things we feel like the students will know, but no, they will not know, because for them it may be a conceptual jump. Okay. So far in this course, we have only been working the stresses along the axis of the force for the normal stresses, and then where the axes were parallel, then we called it as the shear stress, right? But remember, in one of the sessions I talked to you and I said to you, in actual, the stresses will be a 3D quantity, and I showed you that matrix that links them, right? So whenever you have an x stress, you will have a y stress. You will also have a z stress. So it's not about you changing the axis of the force or you changing the coordinate system of the model geometry. No, it's only about calculating the component of the normal stress, because remember that example that I solved in the class where we had two strain gauges, one along x-axis and one along y-axis, right? So now, although the force was being applied only on the x-axis, we still had a strain on the y-axis, and from that strain in the y-axis you can also calculate the stress on the y-axis, along the y-axis, right? So in reality, your full definition of the stresses cannot be completed unless you have x, y and z components as well as the shear components, right? That will then complete the definition. Although for these kind of simple hand calculations, we'll rarely need all of the components, but in other cases where the stress state is, you know, multi-axial, you may have to look into all the components. Okay, so the computer allows you to do this very simply, and all you have to do is right click on the results, again go back to your defined stress plot, and in the defined stress plot choose the component that you are trying to view. So we are trying to view the y component, so just simply choose stress along y normal stress, and that's it, and you will get the y stresses. Keep the other values default, and I'll change the scale to true scale like I said to you for the other one as well. In the chart options, I will plot the maximum and minimum. I'll keep it floating because I'm plotting it in megapascals, and in the other, is there anything else? Yes, I need to change the units to megapascals, and then I'll just click on this tick. And now you can see this distribution that you are seeing is for SY, which means it is the sigma y of the same bar. And you can see here, interestingly, that the y stresses are also maximum along this particular point, and the highest value of y stresses is 35.987. But what is interesting is that as far as this whole thing is concerned, you know, away from the notch, the y stresses are very, very low. You can check the actual values by going into the probe tool and clicking here, right? So you can see here the y stresses are almost 0, right? Can you see that? The y stresses are almost 0 away from the notch, and that is expected, because if you are only pulling it in one direction, then the only Y stresses will be simply because of some Poisson effect. There is no other applied load, nothing else there to cause any significant change of stresses in the Y direction. But where there is stress concentration, that is for example along this edge, now the stress system is no longer uniform. So you are no longer uniformly pulling it in one direction. Some components will go in other directions as well, and they will be significant, because think about it, 35 megapascal is significant, isn't it, compared to 170, 160, although it's not, you know, exactly similar level, but it is still not something that you can simply ignore. You understand? So that's what I want you to plot and reflect. So I want you to plot some of these graphs along with these values later on in this part of the report over here. Here I've said insert contour plots for the 5 quantities. So make sure you insert these plots over here for x, y and z, and then the other von Mises as well. I'll talk about that, and also note down these numbers. So what I will be doing is in the next lab session, now I'm already severely delayed because of repeating all this, but yes, go on.
So the last point what you said for the bottom one, but after we plot the numbers, yeah.
Yes, I said that copy the graphs from there and put them in the report. Screenshot. You can do screenshot or print command from there, okay? But make sure the graphs are readable, okay? The fonts are large enough to read, okay? So put them here as well, okay? So right now maximum normal stress along y-axis is 35.98, and you notice the reason I'm asking you to take the screenshot is because then you will be able to see the locations and compare the locations as well. What you can do quite easily is if you double click on this, on the probe, where did my probe icon go? So I can actually probe the results. I have not asked you to do this, but you can actually note down the node number as well, and then later on compare the values at that node for x and y. But I have not asked you to do this in the report, but this is for you something that you can do. But I will be doing something similar in the next session, okay? Anyways, so let's now close this and go back to our plot, and now also plot stress along about the z-axis. So I again go to define stress plot, and this time I will go and say stress about z-axis, okay? And I'll again plot it on a true scale, also show max min, and keep the units again in megapascals, and okay. And now you can see here the stress along z-axis is actually significant only around the supports, where the supports are. Now in our case, these supports, because we did not model actual support, so they are not necessarily very realistic, so we will not be too much bothered about it. In reality, depending on how you have actually built in, then you may be able to see what the effect of support is. Right now we have completely made it fixed. So if you were to completely fix it, like by putting it inside, let's say, you know, something, and then welding it all around, then this is the kind of stress that you will get. Right. So we will also note down this number, and you can see that this is almost similar to the x-axis stress. So 35.026 or 35.03. Then I've also asked you to note down the von Mises stress, okay? So von Mises stress is something that we will define in the next lecture, but I just want you to right now plot it, and I will talk about this more in the next session. Basically you can calculate the von Mises stress using a formula that I will be talking to you about later. Define stress plot again, and plotting the von Mises stress. True scale, okay, megapascals. Actually, von Mises was already plotted, I think, so I don't need to replot it, but okay, fine. I've done it now, so just show it. And okay, so you can see here, and when you plot von Mises, by default, the software also displays to you the yield strength for comparison purpose. Okay, so this is now the value of the von Mises stress is 166.364 in this case. You can calculate the margin of safety based on von Mises stress as well, and then you can compare that with the factor of safety for this case based on maximum stress. So this will be 351.571 divided by 166.364. So this comes out to be 2.11. Okay, so this is what you can calculate and compare. So after inserting these graphs, you can then calculate your stress concentration factor. And how do you calculate stress concentration factor from the FE analysis? So basically you'll take stress concentration factor, and I've given this formula in the slides anyways, but I'm just writing it for you again here. KT we normally call it, or we can even call it K, depends on the book that you're using. So what is KT? It is the value of maximum stress, right, divided by net stress. Okay, if you are defining it based on net stress. Now again, you need to remember, sometimes the books will define it based on average stress. So every time you look into the stress concentration factor, see what definition they are giving, because then it will end up with different numbers. Okay, for us we are using, because our book is using based on net stress. Okay, so we are using it based on net stress. So this one will become, in our case, what is this? So maximum stress was how much? 173, I think, 0.92 for our this model, because we are keeping now everything for the final model, right? Because we have believed that this is converged and computationally efficient. So 173.92 divided by net stress was how much? 82, I think. So how much it was? 82.6. Yeah. So how much is this now? 82.6. Okay, so 2.10 is our stress concentration. Okay, fine, that's 2.11. Yeah, so right now this is our stress concentration factor, and if you remember in the slides I also showed you the chart, right, based on other people's values, and I want you to basically compare this number from that number, right? And we did that in the class, and our number came out to be on that day around 2.05. Remember? So just compare it with this number. So basically what I am trying to tell you here is that your FE analysis has shown you that the stress concentration factor in this case that you are getting from the charts is approximately same. Okay, there will be minor differences because obviously their data collection, maybe when they did it using experimental methods, or maybe in terms of your reading of the chart, because you're only relying on a very crude grid here to read the chart, right? So if you read it precisely, then probably it will be 2.11. Okay, and I told you that in reality what then this means is that if you have a chart like this, then instead of doing FE analysis all the time, you can correct your results by reading the stress concentration factor from the chart and multiplying it with your hand calculated net stress to simply get the corrected answers for your maximum stress. For the report, you mean the submission? Yes, you exactly do the same thing because your geometry I'm not asking you to change, so really your stress concentration factor will remain same. Okay, so yeah, yeah, you can compare it with my graphs that I have, because I'll upload this anyways on the system now. Okay, but if you, otherwise my original idea was that 4 people so they should do it with 4 materials, but it's okay, I don't want extra work for you. I know it's a very short time right now, so no problem, just compare it with the, if you want, yes, that's fine. But I asked you, I given a further relaxation. I said just choose one material and compare with my graphs. Okay? But if you want to do 2, excellent, no problem. Okay? So that's all about this assignment, and I will now stop this particular record. I think there is nothing else in this left now after this, right? Yeah, so just a bit of discussion and that's it. Right.